Hello, welcome viewers to the NPTEL lecture series on the calculus of variations. This is the 9th lecture of the series. In the last lecture, we discussed several examples as applications of the Euler's theorem, and in the various example series of applications of the theorem. First example, we considered I y, the functional I y as integral 0 to 1 y prime square minus y square dx with the adjoining conditions y 0 equal to 0 and y 1 equal to 1. Comparing it with general form of the functional I y equal to integral x 1 to x 2 f x y y prime dx, we have f as y prime square minus y square, and in this Euler's equation implies that y plus y double prime equal to 0. This differential equation, this is a second order differential equation, and so y is to be assumed that admissible functions will have twice continuous differentiability of this y is to be assumed here, and so y x is the solution of this differential equation y plus y double prime equal to 0 given by a cos x plus b sin x, and the given conditions then imply a equal to 0 and b equal to 1 over sin 1, and so we get as extremals y x equal to sin x by sin 1. In the next example, we had considered I y equal to integral 0 to 1 y prime square plus x y dx. So, here f is y prime square plus x y, and so Euler's equation f y minus d by dx f y prime equal to 0 implies that x minus 2 y double prime equal to 0. So, we get y equal to x cube by 12 plus a x plus b, and these a and b constants will have to be determined by the given conditions. So, we get y 0 equal to 0 implies b equal to 0, and y 1 equal to 1 implies that a equal to 11 by 12. So, we finally get y x equal to 1 by 12 times x cube plus 11. So, that this is the extremal, and in the next example we had considered I y equal to integral x 1 to x 2 of y square dx, and here the given conditions are y at x 1 equal to a and y at x 2 equal to b, where a and b will have to be chosen suitably, and here f is y square, and so Euler's equation f y minus d by dx f y prime equal to 0 implies that y identically 0. So, if a and b are not on the x axis, that means a and b are not equal to 0 0 respectively, then we have these x 1 a and x 2 b not on the x axis, and then there is no solution of this problem in the space of continuous functions. Only solution to this problem is a discontinuous function given by this figure here, and so we do not have extremal in general in the space of admissible curves. Here in the next example, we considered I y equal to integral x 1 to x 2 m plus n y prime. M and n are functions of x and y here. So, f is m plus n y prime, and so Euler's equation implies that m y minus n x equal to 0, and so here this will have to be solved for x y or y as a function of x, and so the solution of this equation is a curve, and in general it may not pass through these given points x 1 y 1 and x 2 y 2. So, there will not be a solution of this problem in general, and if it has, then there is only one curve which is passing through those 2 points. And in the second case, when m y minus n x is an identity, m y minus n x equal to 0, if it is an identity, then we see that the integrand can be written as m d x plus n d y, and it is an exact differential, and so by the property of exact differential there exists a function u of x y such that the total derivative of u is equal to m d x plus n d y, and so here this integral finally becomes the values of u at these endpoints. So, u x 2 comma y of x 2 and minus u of x 1 comma y of x 1, and so this is a fixed value, and so this is not a problem of the calculus of variations. Next, we considered I y equal to integral 0 to 1 y square plus x square y prime dx. Here y 0 equal to a and y 1 equal to b, then f is y square plus x square y prime, and so Euler's equation implies that y equal to x. So, if this 0 a and 1 b are not on the diagonal y equal to x, then there will not be any solution here. So, it is only for the case when a equal to 0 and b equal to 1, we have this y equal to x as an extremal of this problem. In the next problem, next example, we considered I y equal to integral x 1 to x 2 y plus x y prime dx, and again with those same conditions, y at x 1 equal to a and y at x 2 equal to b. F is here y plus x y prime, and we see that here we get m y minus n x reduces to identity, here 1 minus 1 equal to 0. And so, here we see that this is an exact differential, which can be seen that it is actually d of x y, and so we get this integral x 1 to x 2 d of x y as x y evaluated at x 1 to x 2. So, that is x 2 y at x 2 minus x 1 at y at x 1, which is a fixed quantity, and so this is not a problem of the calculus of variation. So, that is where we had arrived at the in the last lecture. Now, we consider here special cases of this functional. Of the functional I y, which is actually equal to integral x 1 to x 2 f x y y prime dx. So, when some of the variables are not present, then we get special cases. The first special case we consider here, that here f, see in general f is function of x, y, y prime. So, let us say this is only function of y prime. So, here x and y do not appear explicitly. In f, and so in this case we have f y minus d by dx of f y prime equal to 0, implies that d by dx of f y prime equal to 0. Now, this is only function of y prime, and so this implies that f y prime y double prime equal to 0. So, either, so this implies if, so if this f y prime, this is also a function of y prime, if this is not equal to 0, then y double prime must be equal to 0, which implies that y equal to a x plus b. So, we get a straight line as extremal, and so here we get family of straight lines for different values of a and b, we will get different lines, and then these a and b are to be determined by the given condition. So, here the extremal is a straight line if this f y prime is not equal to 0. If this f y prime which is a function of y prime is 0, then we find the roots of this equation. So, let us say let k be a root, a real root, then we have, that is, then y prime equal to k such that f y prime k equal to 0. So, for any root of this equation like this, f y prime k equal to 0, we get y prime k. So, y prime equal to k. So, y prime equal to k implies that y equal to k x plus some constant c here. So, here this c is to be then determined by the given condition here, and k is determined from this equation again. So, again we get a straight line as an extremal. So, in all these cases where this f y prime is not equal to 0, we get an extremal as straight line, and if f y prime is 0, then we find the roots of this equation, and let us say if y prime equal k, if k is a root of this, then y prime equal to k, and we get y equal to k x plus c. Again we get a straight line as an extremal of this the Euler's equation as a solution of this. Now, here let us see various examples of this case. The first one is let us say this is 9.1. So, here this L or length of y is given by x 1 to x 2 square root 1 plus y prime square dx. Here as before, we have these 2 points a and b, and this is the curve joining these 2 points, and this is x 1, this is x 2, this point is x 1 y 1, and this is x 2 y 2, and so this gives you the length of this curve. Now, here we have, since this is a function of, so f here is square root 1 plus y prime square, and this is a function of y prime only like this. So, we get here, so we should have f y prime y double prime as 0. So, that is the Euler's equation, and so in this case here f y prime is 1 over square root 1 plus y prime square, the 2 and then times 2 y prime. So, 2 will cancel. So, we will have y prime over square root 1 plus y prime square. Then again we differentiate partially here. Here of course, it is a only y prime is a variable. So, it is ordinary derivative of that with respect to y prime. So, we get here 1 over, so like this. So, we get here 1 and into this 1 plus y prime square minus y prime over to 1 over this square root 1 plus y prime square, and then y prime here over, you get 1 plus y prime square. So, this becomes, so here we get again, see, you will have this as 1 plus y prime square minus y prime square over 1 plus y prime square to the power 3 by 2, but 1 over 1 plus y prime square to the power 3 by 2. So, this is not 0, and therefore, hence this f y prime y double prime equal to 0 implies that y double prime equal to 0, which implies that y equal to a x plus b. So, we get extremal as straight line as expected. So, in the another case of this, we have seen that like if we take t as time taken by a particle moving along y, then we know that this is given by x 1 to x 2 ds by v, where this v is the velocity of the particle along the moving along the curve, and so in general this v is a function of x y y prime usually, but in particular case if we take, let us say, if v is a function of y prime only. So, in general this, let me write the general dependence. So, here usually this v would be a function of x, y and y prime, and so this would be like x 1 to x 2 square root 1 plus y prime square over v x y y prime dx. So, that is the general form of the functional, which gives you the time along a given curve here. So, you have these 2 points A and B, and particle is moving along this curve y x, and here v is the velocity, which is a function of these 3 variables in general. So, if v x y y prime is function of y prime only, like in the case where it is moving in a plane where then gravitational force is not playing any role, then it will velocity will be just v y prime only. So, that can be taken as the function of y prime. So, in this particular case we have t as x 1 to x 2 square root 1 plus y prime square over here v of y prime. So, here again this f is just function of, so in general x y y prime, this is a function of y prime only, which is nothing but square root 1 plus y prime square over v of y prime. So, here in this case, so we so therefore, the an extremal will be a straight line. Now, the next one, so it was 9.1 here. Okay. So, let us call it 9.2. So, in this case, if we consider this t y as x 1 to x 2 square root 1 plus y prime square, and then velocity as a function of x, let us take here x itself for particular case. So, v of x y y prime is x here. So, in this case here f is function of x and y prime only, which is square root 1 plus y prime square over x. So, this is case 2. So, let us say this is case 2 where f is function of x and y prime only. So, this is an example of this case. So, here how do we do this? So, here Euler's equation is, which is f y minus d by dx f y prime equal to 0, implies that minus d by dx of f y prime as before, because this f, since f y is 0, and so we get this f y prime equal to, which is function of x and y prime as the first integral. So, this Euler's equation gets integrated easily. Here we get f y prime as a function of x y prime equal to c 1, and then once more we integrate it to get the extremals. So, let us apply this case to this example. So, here we have f equal to square root 1 plus y prime square over x. So, here so f y prime equal to c 1 implies that 1 over x, then 1 over 2 root 1 plus y prime square into then 2 y prime equal to c 1. So, we get 2 cancels. So, y prime over square root 1 plus y prime square equal to c 1 x. So, here we will try to get parametric form of the equation. So, x, so this implies that x equal to 1 over c 1 y prime over square root 1 plus y prime square. So, we substitute y prime equal to something, and then we will try to get the solution here. So, if we take y prime equal to, let y prime equal to tan t, t is a parameter here, then we see that x equal to, then x equal to 1 over c 1 tan t over here square root 1 plus tan square t. So, that is over, this is sec square t. So, sec t second t, and this is sin t upon cos t into sec t. So, this cancels. So, you get 1 over c 1 here. So, c 1 tilde sin t. So, that will be the x solution here. And so, now to get y solution here, we know that this dy by dt equal to dy by dx upon dt by dx by dt. So, that this is tan t, and here this dy by dt dy by dt will be then So, dx by dt, x is this. So, that will be C1 tilde here. So, cos t. So, that will be x equal to C1 sin t and dy by. So, 1. So, this will be actually, let me. So, here dy by dt is dy by dx into dx by dt, which will be dy by dt up into here dx by dt is C1 tilde cos t, and so dy by dx, sorry, which is C1 tilde dy by dx is tan t into cos t. So, that is C1 tilde sin t, and therefore, y equal to C1 tilde cos t plus C2. So, we get this as solution here, and so we have x equal to C1 tilde sin t and y equal to C1 tilde cos t plus C2. So, eliminating t from here gives you x square plus y minus C2 square equal to C1 tilde square. So, we get circles as the extremals. The family of circles, 2 parameter family of circles here, and then C1 and C2 are to be determined by the given conditions. So, here we get these circles as the extremals for this case. Now, the next case where we get this f, which is in general x y y prime, which is a function of y and y prime only. X variable is missing here. X does not appear explicitly. So, here f y minus d by dx of f y prime will be equal to, in this case, f y minus d by dx of this d by dx, which is a function of y and y prime, and so this is equal to f y minus f y y prime minus f y, sorry, this is f y prime. So, let me rewrite it again. So, this f y, which is also a function of y and y prime, and minus d by dx of f y comma y prime, and so this is equal to f y. We will not write the dependence over y and y prime here explicitly, and so this is d by dx of this thing, which is opening this here. So, we get f y, and then since this is a total derivative, so here variables will have to be then differentiated with respect to x. So, f y partial derivative of with respect to y and then y differentiated with respect to x. So, you get y prime minus here, sorry, this is f y prime. So, y prime y, and then you have y prime minus f y prime y prime y double prime, like this. So, if we multiply this thing by y prime, since this is actually equal to 0, this is equal to 0. So, if y prime is not equal to 0, then you see that y prime this here will be then y prime f y minus f y prime y y prime minus f y prime y double prime. This is 0. So, writing in expanded form. So, you have y prime f y minus f y prime y prime square minus f y prime into, we will write these, okay, y prime y double prime equal to 0. So, let us write this also in the same order, f y and y prime. So, multiplying by y prime we get this. Now, we observe that this d by dx of f minus y prime f y prime is actually equal to, since f is a function of y and y prime. So, here f y prime plus f y prime y double prime, and here the second term minus first we so we get f y prime and then y double prime. So, here we have differentiated y prime and this taken as factor here out, and then minus y prime and derivative of f y prime with respect to x totally. So, here that will be f y prime y and y prime. So, you get y prime square here minus y prime and then f y prime and y double prime. So, that is what we will write it here equal to 0. So, we see that these two are the same because this cancels here and this is same thing as, let us say this is 9.3 and this is 9.4 rather 9.2 9.3. So, from 9.3 and 9.4 we see that this first integral, the first integral of Euler's equation in this case when f x y y prime is actually f y and y prime, function of y and y prime only is given by f minus y prime f y prime equal to C1. So, first integral is readily available here and then this can be integrated once more to get the extremals. So, let us see this is this case in certain examples. So, here say example 9.5. So, here we consider the case where this is x axis, y axis and z axis, and let us say there is a curve given here. This is from x1 to x2, and then this curve is rotated about x axis. So, we get like this surface generated like this. Now, here if we consider ds element here, and then we see that this strip ds strip is rotated like this. So, area of this ds strip will be given by 2 pi y ds, y is the vertical length here. So, area of the area of strip ds revolved about x axis is 2 pi y ds. So, total area, surface area will be given by 2 pi integral x1 to x2 y ds. So, this can be seen like you have x y. So, this curve was like this is ds element here and this is y distance here. So, this gets rotated like this ds element. So, therefore, this is 2 pi x1 to x2, this is here x1 and this is x2. Y ds is given by 1 plus y prime square dx. So, that is the surface area of this of the object obtained by revolving this curve about the x axis. So, here f is x, y prime in general is given by 2 pi y square root 1 plus y prime square, which is function of y and y prime only. So, we see that hence the first integral of Euler's equation is given by f minus y prime f of y prime equal to c1. Which gives us in this example. So, 2 pi we will observe in C1 itself, and we will have y square root 1 plus y prime square minus. So, let us write 2 pi also here minus y prime and then this. So, 2 pi f y prime means 1 over 2 root 1 plus y prime square and then 2 y prime equal to C1. So, this 2 will cancel with this and 2 pi taken on the other side. So, we will have y square root 1 plus y prime square minus y prime square over square root 1 plus y prime square. equal to C1 over 2 pi, which is written as C1 tilde. So, here 2 pi y should also be there, which I missed. Into y prime. Y prime, this factor is coming from here. So, taking the LCM here, we get this term will cancel. So, we will have y into 1 plus y prime square minus y prime square equal to C1 tilde, which implies that y over square root 1 plus y prime square equal to C1. So, here again we write in the form, we take parametric representation. So, we have y over square root 1 plus y prime square equal to C1 tilde, and if we take let y prime equal to sine hyperbolic t, we see that this implies that y equal to C1 tilde, you get cos hyperbolic t. So, y comes out in this parametric form, and now to get dx by dt is dx over dy into dy by dt like this. So, this dx by dt comes out to be, so this is 1 over sine hyperbolic t, and dy by dt is, because y is this, you get C1 tilde sine hyperbolic t, and so this you get only C1 tilde. So, hence x comes out to be C1 tilde t plus C2. Thus, in the parametric form we have x equal to C1 tilde t plus C2 and y equal to C1 tilde cos hyperbolic t. Now, this t can be eliminated here. We get y as a function of x, this C1 tilde cos hyperbolic x minus C2 over C1 tilde. So, writing in a standard form, we can write that y equal to a cos hyperbolic x plus some b over a, like that. So, that is the form of solution which tells us that it is catenary. So, this is a catenary, which is, and the surface, thus the surface of revolution is called catenoid So, in this case the extremals are catenary here. Those are the curves which will minimize the surface area. Now, we come to the problem of Rochester cone, which was introduced in the first lecture. So, here recall that T y is x 1 to x 2 square root 1 plus y prime square. We had got root 2 g here and then root y. So, over root y dx. So, here f is 1 over root 2 g root 1 plus y prime square over y. So, this is again a function of y and y prime. So, the first integral of Euler's equation in this case is f minus y prime f y prime equal to C 1. So, here you will have 1 over root 2 g square root 1 plus y prime square over y minus y prime over root y we can take out here, and you have 1 over 2 root 1 plus y prime square and again 2 y prime equal to C 1, 1 over root 2 g here also. So, taking this 1 over root 2 g on the other side, merging it with C 1 and simplifying this, we get the following in this case. So, this okay. So, let us write it 1 plus y prime square over root y here minus, you get this 2 cancels here, y prime square over root y into root 1 plus y prime square is C 1 tilde here. And we can see that in this case you will have 1 over root y is taken out, and then you have 1 plus y prime square minus y prime square over root 1 plus y prime square equal to C 1 tilde. So, this is cancelled here. So, we get 1 over squaring it, we get y into 1 plus y prime square equal to C 1 tilde, or inverting it we get y into 1 plus y prime square equal to, let us say, constant a, where a is 1 over C 1 tilde. So, we get in this case y into 1 plus y prime square equal to a, and so y is a over 1 plus y prime square. So, if you take y prime equal to cotangent t here as a parametric representation, we see that y comes out to be a. So, this gives you cosec square. So, you get sin square t here, and then writing it as using the formula cos 2 t equal to 1 minus 2 sin square t. So, this implies that sin square t is 1 minus cos 2t by 2. So, we get y as a into a by 2 to 1 minus cos 2t. Then we need to get x in terms of t. So, dx by dt is same thing as dx by dy, and then dy by dt here. Okay. So, dx over dy is then inverse of that. So, tan t, and dy by dt will be into a by 2, and then you have differentiation of this will give you plus sign, and here you have sin 2t into 2. So, this gives you tan t a into tan t into sin 2t. So, this is 2a sin t, and you will have this upon cos t into sin t cos t cancel. So, 2a sin square t. So, then writing this as again a and 2 sin square t as 1 minus, because sin square t is written here, 2 sin square t as 1 minus cos 2t. So, we get dx by dt as a times 1 minus cos 2t. Integrating this, we get x equal to a into, so we write a by 2 and here 2t, and then you get minus sin 2t by 2, and so that 2 we have taken out. So, we get the parametric form like this. Thus, x is a by 2, 2t we write as t tilde minus sin t tilde, and where t tilde is 2t, and y equal to a by 2 into 1 minus cos t tilde. And we know that this is the solution of this curve is called cycloid. So, extremals are cycloid in this case, which is as expected, which was mentioned in the first lecture. So, next we will be considering the functionals which will have more variables and more dependent variables and their higher order derivatives, and then finally, we will be considering the functionals which will have more independent variables and functions of those independent variables. That will be considered in the next lecture. Thank you very much for viewing this.